Hello everyone, today I'm going to present my paper, an intermittent OTA approach to update the deep learning weights on energy harvesting devices. Here's some information about me. My name is Wei, a second-year PhD student at the University of Texas at San Antonio. Department of Computer Science. My research interests including IoT, distributed learning, energy harvesting, deep learning, and intermittent updates. Currently, I'm actively working on various approaches to improve update efficiency to resource-constrained IoT devices, especially for energy harvesting scenarios. Before I joined the PhD program, I earned my master's degree in computer engineering and had 3 years of industry experience as a software engineer building end-to-end IoT solutions. Here's the outline of this paper. First, I will introduce the background, and I will go to the motivation. Then I will go through the system overview, then jump into the core part of this presentation, which is an intermittent OTA approach. And then I will go over the experimental setup. Then finally, we evaluate our result, then goes to conclusion. Let's first go over the background. IoT solutions has been widely used in different areas, including logistics, industrial automation, medical health monitor, smart building, transportation, smart home, energy saving, and smart agricultures. However, in these IoT solutions, they tend to do the centralized AI algorithms, which means all the data in the edge device has to be transferred to the cloud for the deep learning algorithm to make smart decisions. However, as the time goes, the current trend of IoT solutions are tend to move the AI algorithm from the cloud to the localized IoT device. There are three reasons to moving the AI algorithm from cloud to the local. The first one is due to communication. Communication is energy consuming. To transfer the data from local to the cloud, a lot of energy is required. As nowadays the data collected by IoT devices become big and big, then we consider the data to be big data already at this moment. If we can do the algorithm on the local instead of cloud, so we don't have to send all the big data to the cloud. So a lot of energy can be saved, especially if we run with energy harvesting so power supplies. It's crucial to use as less energy as possible. The second reason is due to the privacy. Nowadays, a lot of AI algorithms are based on the personal private data, such as recommendation systems. Those data are sensitive, and the customers or end users, they do not want this data to be exposed to others. So they want to keep this data private. So there's a need to that's why there's a need to keep the data local, and therefore, as a result, the AI algorithm has to be run locally. The third reason is a real-time response. Some AI applications, such as the self-driving car, which requires instant response to the action as happened in the end user side. If an AI algorithm is running on the cloud, there will be at least certain latency is required for the data to transfer to the cloud, and the cloud send bad response. There's at least a gap between the decision and response. So if some action like tap the brake has to be happen at right now, and if we wait until the decision made by the cloud, it's too late. So there is a need to implement some AI algorithms on the end device. Some people may think energy harvesting may not be common in our daily lives, but actually they have some pretty interesting use cases. For the first one, you can see this is used for wildlife tracking. Some small devices implanted into birds, so we can track where the birds were located. This is especially important to track the birds' migrations. The second one, you can see some kind of device is put into the oceans, which is considered to be extreme environment because of the salt waters. which is can cause damage to metals. So some kind of image harvesting device can be implemented in this case to monitor the harsh environments. And also you can see on the third image, some kind of device image harvesting device is printed even on human skins, which can monitor some temperature data or etc. some vital data from human bodies. And also this on the first image is a smart lens, which can monitor the tear glucose, which can eventually use for some medical to check for medical issues such as checking diabetes. And also energy harvesting can be used for farming. This cloud has some kind of device implanted, so where the cow can be so it can be used for animal trackings. And the last one will be smart darts, which is the future of the IoT solutions. You see this tiny device is very little. This device can put in almost anywhere. That can used to be monitor sensing data such as temperature or etc. Or maybe if it's possible, you can use to do some computing as well. That's an excellent solution. Let's talk about the motivation to adapt the keep changing environments, or to adapt the new user requirement, or try to improve the deep learning model accuracy. Code update is one of the most important features. It must to be implemented into the IoT device, which can prolong the life of deployed IoT device. It can improve the performance of the IoT device as well. However, there are basically two challenges to enable the code update features. The first challenge is due to the high energy consumption. You can see this graph. The energy consumption of IoT devices keep growing. However, the energy can provided by the battery is growing much slower than the energy actually required by IoT device. And so as a result, as the energy harvesting IoT device, the energy can harvest with the energy harvest technology even less than the actual battery can provide, which is a big gap between the energy that can actually be harvested and the energy required for the computing. Therefore, as a result, for energy harvesting IoT devices, they has to be run intermittently, which means they have to be run with the power. It has to be able to run between power failures. As we can see from this image, only limited power can be harvested from human bodies. If some sensor is rely on this harvested power from a human body, they can cause frequent power failures. Here's the second, will be the second challenge. Frequent power outage can cause frequent update failures. Once the update failure, and next time when the device boot up, the update process of the previous power cycle will be completely lost. There are two existing approaches to do over-the-air updates. The first one is called image update, which requires the entire image to be transferred from edge server to the IoT device, which requires relatively large amount of memory to store the entire image, and which is not the case in IoT solutions, which has limited memory space. The second approach is incremental updates, which divide the whole image into small pieces, and each time we only update one piece of it. And this approach is also not optimal as well, because if update if update in during a piece update, if the update failures, the process of this piece update will be completely lost. Next time we have to start this piece update from the beginning again. There's a lot of energy is wasted. Here comes with our approach intermittent updates to limit the number of data need to transfer from edge server to the IoT device. In our approach, in our case, we only consider one of the most important deep learning updates, which is weight updates. And we hope our future work will continue to work We will continue to work the other type of deep learning updates, such as model updates. We hope our future work will solve the issue. Let's look at our system overview. First, let's look at how a typical update process works from edge server to IoT device. The differencing algorithm will run on edge server, compare the difference between new deep learning models and the old one, which will, in this case will be compare the difference between matrices of the old one and matrices of the new one. Then transfer the update packet through over the air communication, and once the IoT device receives the update packet, then store temporarily into RAM, then decode and update into the FRAM. Then we propose, this here comes with our detailed proposed strategy. First one will be the data encoding, which will reduce the number of data need to be sent through the cloud to the IoT device. Then we optimize the transfer process, which will reduce the energy consumption by the transmission itself. Then we propose the third tech strategy, which is runtime support that will enable the intermittent update process. Let's talk about our first strategy, data encoding. In our approach, we only consider the weight updates between two versions. The weight matrix structure will remain the same. In order to find a difference, we can simply compare weight matrix one by one. We can find the difference. However, if we directly send this information to the IoT device, there's a big data overhead. It not only requires the index of weight matrix, but also requires the index of the location within the matrix. Here's how we do it to reduce the size. We merge all the weight matrix of a model into a big one, so we can eliminate the matrix index. Then we further divide the merged matrix into different sections. So the higher bits of the index can be combined together, and we only require send once within a sections. Then we further divide the section into different blocks. Each block will contain continuous data points. So for the index of each point, we can just simply send the first index of the points. Then we can, based on the length, we can calculate the actual index of the associated points. This can eliminate the index required by the differencing algorithms. And also we reserve one bit, the first bit of section, and also reserve the first bit of the block as used for the second strategy. Our second strategy is data transmission optimization, which will minimize the communication cost. So in this graph, this is how a typical communication works. This is an example of Bluetooth Low Energy, which is the BLE. That is the communication protocol we use to do the communication in our experiments. So in this image, you can see basically there is almost no energy is consumed while the BLE is on sleep mode. Once the device wake up, it has to go through a wake up stage, which will consume a certain amount of power, and jump into RxTA stage, which is the stage to sending and receiving data. Then has to go through a processing stage, which will store the data received into the local memory. Then go through some kind of stage to go back to sleep mode. You can see for each power cycle, each communication cycle, there is a certain amount of energy wasted to wake up and go before sleep. If we try to maximize the energy used for communication, we need to maximize the number of RxTS can do within one communications. And for BLE, there's a maximum packet size there's a maximum packet size which is defined by the protocol. In order to maximize the communication cost, we need to maximize the packet size. As shown in the previous slide, we reserve one bit from the section and one bit from the block. So then we can combine different sections into one packet. So there's one communication power cycle can be saved. A tip how then on the right side image it shows how a typical communication works. So we try to limit the communication cost. So once there is an update available, the ISO will notify the edge device there is an update available, and the edge device will decide when to request the update. The previous two strategies is used to save the energy consumption, and our third strategy, runtime support, is the one used to enable intermittent updates. Here's how a typical runtime support works. Once the power on, let's go through its initialization stage. Then we'll check if there is a backup available. If yes, then resume the state. We can resume our updates. Then if not, we can jump into our regular tasks. Then if there is an update notification is counseling, it will be interrupt the regular task and goes to checking the energy. If there is enough energy, we will try to do the update. Then we can try to select the update time, which will be sometime wait until the previous task to finish. Then the device can have more resource to do the updates. Then here comes in how here will be the transfer, the update transmit and updates. Now after the LT device receive the update, we will track the energy again to see if there is enough energy to do the decoding and updates. If not, then we will store the information back up. Then we'll power out. Then we'll wait next power cycle to do the update. So here's our experimental setup. We use Sigland SDG 1032X function generator to act as energy harvesting power supplies. We combine CC2640 and MSP430 5994 together to act as an IoT device. CC2640 is a BLE communication, and the other one is used for communication. And we use Raspberry Pi as an edge server. Then here's our evaluation. Since this is the first work to actually enable the intermittent update process, so we only compare our proposed approach with there is no intermittent updates available. We evaluate our performance based on the update time and capacity size. You can see when the capacity size is small, we can have a relatively good performance. As the capacity size getting larger, the performance decrease. It's because of there is once the capacitor size getting larger, less frequently we will have power failures. And also compare with the baseline, our proposed approach will always have a better performance. And our second image shows the bit array. Since the IoT devices are usually put into extreme environment, which have a higher error rate, you can see this trend. So our proposed approach is also works in this situation well as well. We have discussed the need and challenge to enable over-the-air updates, and also present an efficient over-the-air intermittent update approach on our experimental setup. And we analyze the performance of the approach based on the total update size and the capacitor size. The result shows that the proposed approach can reduce the number of update times up to 44%, compared with no implemented with our approach. That's the end of my presentation. Thank you.